Thank you. This was actually supposed to be presented by Professor Bill Cowley, but he couldn't make it, so although my name's on it, I really have nothing to do with this work, so all the credit goes to them. Bit of an overview. I'll look at an overview of SUSat. So SUSat is just the name of our QB50 satellite. So this is actually a QB50 comms system. We'll then look at the requirements and aims, the comms payload itself, or the communication system, and then some ground station information, then some examples and the current status, and then just some acknowledgements. Actually, the acknowledgements at the front, those are the partners, the various funding agencies and various organisations who have contributed either financially or in kind to this. Okay, so a bit of how it's split up. So the University of Adelaide is the project lead, and the University of South Australia are responsible for doing the comm system, both the ground station and the modem. So I'm the project lead of the whole project, and of course of the University of Adelaide side, and Bill Cowley runs the University of South Australia side. So these universities are maybe 15 k's apart, just for geographical context. The responsibilities, so we're doing the structures, the systems engineering, the structure, ADCS, and our experimental, our secondary payload, which is called MASP, which is a atmospheric species measurement system based on dual frequency GPS delay. And the University of South Australia, as I mentioned, doing the comms payload and the ground segment. So just a bit about our satellite. Onboard computer and EPS are both COTS systems. The structure is custom designed, the ADCS is custom designed, the comm system is custom designed, as is the obviously the secondary payload and the flying and INMS. So a bit about the coding issues. So modern communication systems use channel coding to improve the gain, and you can get up to 10 dB gain depending on your coding structure. So for uplink, it's a little bit difficult because on the receive side you need to have a fair bit of compute power, and because the satellites or the CubeSats don't have a lot of onboard compute power, getting good channel coding on the uplink is a little bit difficult. But fortunately there's not much data going up, or particularly in our case there isn't. On the downlink side it's much easier to implement because the ground station can have as much compute power as you want. So I guess the takeaway message here is that for nanosats, channel coding on the downlink is good, on uplink not so much. So AX25 uses byte stuffing, which gives it variable length packets, so it's not really suited to channel coding. As a result, we use the CubeSat space protocol. The requirements, so these are basically not necessarily QB50 requirements, but our requirements are, so the comm system has to provide the TT&C and scientific data download. We're using a 70 centimeter and 2 meter amateur bands, and we cater for multiple ground stations. So aims are to allow FSK and flexible bit rates, so we want to vary the duty cycles and transmit and receive transmit rate power, and include channel coding for error correction. Obviously, it needs to be low mass and low power, as all nanosat systems. Use a software-defined radio, and also the possibility of inter-satellite links. So this is kind of a secondary goal. At this stage, obviously, the primary goal is to just get the data down to the ground station, but we're also very interested in exploring inter-satellite links, and in fact are looking for potential partners, although it's very late in the piece, I understand. Some specs, about 1200 to 9600 bits per second. So the transmit power is about 100 milliwatts, so the DC power is about 500 milliwatts for TX and about 50 for receive. We use the CubeSat space protocol with a custom layer 2 and channel coding. And we also use GPS frame timing, so use the GPS to synchronize the downlink. It's not necessary, it can be done without it, and that's important because our GPS is not on the whole time. We turn it on for a certain amount of time, and then we propagate the trajectory forward and then turn it off. So some passes at the ground station we would have GPS for use, and other times we would not. And these, the comm system can be configured for either VHF or UHF. And again, the software-defined radio on the ground station. This is the first prototype. So this is actually quite similar to the two presentations we just saw before. So it uses an MSP 430 microcontroller, a TI RF integrated circuits. We use I2C or UART interfaces, and then I guess the other MSP GCC toolchain is used. So this shows the first board as well as some other pieces of hardware required to interface it like a JTAG system and that kind of thing. So this shows an example of an experiment where we kept the receiver stationary and we took the transmitter for a walk around, and we just varied the amount of gain to see and then measure sort of bit error rates and those sorts of things. And this is actually available on the website of the University of South Australia. So the University of South Australia has a research centre called the ITR, Institute for Telecommunications Research, and they are the ones who are doing this work. So their website's got a whole lot of information about this. This is currently this is the third iteration, which has actually been sent for fabrication now. And that's on the right, and on the left-hand side we've got a TINSAT, which is just used to check what the antenna distribution was like. The tests, so far we've got a high altitude balloon test which was supposed to have launched at the end of October, but due to weather we weren't able to launch, so the launch is actually scheduled for November 1. So this is actually the second version of the board, and the only difference between the second and third is there were a couple of errors made, and so there were just a couple of jumper wires on it, but otherwise it's basically the same the same system. So that's all packaged up, ready to go on a balloon. So this balloon goes to about 80,000 feet, so and it sort of lasts about 2.5 hours. So it's a good opportunity to test the comm system. On the right hand side is the results from a low density parity test, and it shows basically to get a bit error rate of 10 to the minus 5, I think, or 6. You get you need 4 dB power. And that compares to about 9.5 if you don't have error coding. So basically you've got a 5 dB gain from using channel coding. A bit about the ground station. So the ITR, as I said, they run a fairly big facility, and they do a lot of ground station work for, I mean, they did it for ATV, they did it for SpaceX, they did a number of projects for big international partners, and they have a dedicated lab for the ground station services. It's got an X-band antenna and an S-band antenna, and then a couple of Yagis, and you can see them on. That's basically the ones that we're going to use. So just as I said, we've got a VHF and UHF. So essentially, this board just gets printed twice, and it's small enough so that you can fit 2 of them on one 100 by 100 QB50 compliant board. So we basically have both UHF and VHF, which serves both as a backup, but also the ability to use both UHF and VHF. Then a bit about the ground station. I guess I'll let you read the stuff on the left. I guess the important bit is a custom layer of layer 2 protocol, and that sort of shows what the split packet structure looks like. So basically the idea is to have a small fraction of the frame allocated to uplink, and during the passes over Adelaide, CSP will handle any drop packets. The passes can also be, so data can also be collected from any ground station you like. Basically you would just download a WAV file and then send it to us, and we would decode it. And if there were any errors in that data, we would be able to request that information or those dropped bits as it passed over Adelaide next. So we basically have a primary ground station which has all the capability, and then anyone else can operate as a secondary ground station for us. And then just some acknowledgements, just a benevolent fund, the Sir Ross and Sir Keith Smith Fund, and the South Australian Government put a fair bit of money into the development of this, as well as a number of students. Now the other thing that if we're still interested in is having other people fly our comm system, and we can try some into satellite link experiments. I understand everyone's done their CDR, so of course nobody is going to change their hardware now. But if anyone is interested, please get in touch with me and we can chat about it. That's all. Thank you.
Thank you very much. Do we have questions? Awesome, please.
Yeah. Do you use time scheduling or position scheduling for your ground station passes? If you want to download over a certain ground station, like a radioamateur ground station, and you want to schedule it in advance, you use timing or position from GPS or PD propagation?
Well, I guess it could be either, because we have an orbit propagator, so you could say a time from now to there, and that'll effectively mean a position. But I guess we haven't nailed down exactly how we'll do that. But basically, it could either be timed or from a position.
Thank you.
Any other question? So this concludes our morning session. Thank you very much.